Perfect. How is everybody? How questions, homework, what is next? Homework 2, anything? All good? Perfect. So basically we want to continue with linear programming today, but I want to play a bit with probability before kind of paving the ground to the very cool algorithms that we are going to see. But I'm going to ask you a question that will look, to start with, very, very, very unrelated. And let's have a backup here, just why not? Mm. Okay, here is the code that I want you to take a look at. You don't need me so large here.
Question because our team want to end. Thank you.
Yeah, so m equal minus infinity, counter equals 0. I'm going to count how many times m is going to be updated. M is keeping the maximum values that I've seen so far. It's a code for keeping track of what is the maximum value seen so far. So let's write it down. Keep track of the max seen so far. So what I'm doing n times is at every iteration, I'm picking some random number x in the range 0 to 1. It's a float, can be anything in between. And if x is larger than m, then I'm increasing the counter by 1, and I'll update m. And my question is, how many times will m be updated? And what is a worst case? That what's the maximum number of times that m is updated? That is, what is the value of counter at the end?
It would just end up being n because let's say it goes from 0 to 1 each iteration.
It can be that m is getting larger and larger at each iteration. That x each time is larger than the previous one, larger than the previous one, and so on. Okay. And so the maximum value is n, and I'm asking what is the so the worst case number could be the worst case could be n. Okay, everybody copied it. I need the or let's give a try to. Let's see how this works for us. I want to write another code, kind of similar to this code, and I'll pick, let A be a array A between 1 and n, containing, actually I can go directly of containing now the numbers. How does it look, this new whiteboard? Maybe containing the numbers 1 ... to n, but at a random order. I don't know at which order they appeared, so possibly A will be the array of 4, 2, 4, 2, 3, 1. This is the arrays, the values that I stored in A, and very similar to what we did beforehand, m will be minus infinity, ctr equals 0, and for I goes from 1 ... to n. Now I'll do, instead of picking a random number, I'll say if m is smaller than ai, m should still keeps the maximum that I see in the array, and if m is smaller than ai, then counter plus plus, and m equals to ai. And I'm asking the very same question: how many times do I update m in the worst case? What you have here is some random permutation of the numbers, and every permutation might appear here. Maybe a is the numbers 1, 2, 3, 4 in an increasing order. Maybe they appear in a decreasing order. I have no idea. Every permutation is equally likely. So every permutation of these numbers have the same chance of appearing. By the way, if there are 4 numbers, how many permutations are there? Not very hard, right? 4 factorial, right? We have 4 factorials or n factorials, many permutations in general, right? Because 4 needs to pick a place here, so it has 4 options times 3 heads, 3 options. After we placed 4, 1 has only 2 options, and then 1 doesn't have options at all. Okay, same question. What's the maximum value that the counter could appear, that I update the counter?
It could end up being
It could be that every iteration, if the permutation is 1, 2, 3, 4, if that's what A contains, then every update, for every I, M is updated and the counter is increased. If the permutation is 4, 3, 2, 1, then I M start in the first iteration as 4 and never updated. But so far I didn't say anything too surprising. Now, hopefully everybody has this code written. For this particular code, I'm asking what is the probability, new notation. I'm going to ask what is the probability that it's the second step. Second step is I equals 2. We updated M. All readable? Yeah. Dirty but readable. What is the probability? When I was 1 at the code before, for sure I updated M. Here is a code for I goes from 1 to n. If ai is smaller than m, then m equals ai. M equals ai. And we update the counter. So for this particular loop, I'm asking for when I was 1, since I started when m is as minus infinity, when I was 1, definitely I updated m. No options about it. My question is, what's the chances that in the second step I updated m? And this might be a really nasty question or really easy question, depending on how we looked at it. Here is one way to solve it. What I have, A contains a number, say 1, 2, 3, 4. A contains the numbers 1, 2, 3, 4 in some permutation. 2, 1, 3, 4, some permutation, and then I'm asking the chances that at the second step I updated it depends somehow on which number I picked. In the first number, if my first number that I picked is very large and the probability maybe is very small, but then on the other hand I need to weight it because maybe I picked it the first number as very small, the second one as. That's a wrong way to ask it, because next time I'm asking you what will be the probability in the third case and in the fourth case, and that would be the wrong way to think about this problem. And the right way to think about this problem is to use something called backward analysis that we'll see a few times in this course. And backward analysis is a mental trick that help us build very simple algorithms with very simple analysis. And once we'll see it working, you will be puzzled of why it took people so many years to come up with this trick. So anybody see the answer before I'm getting backward? What should be the answer? What's the probability that at the second step I update AI? Hint, do not use backward analysis. So, I mean, all you know is that the two numbers are a. Of course, you need to ask what's in what. I told you that A sits in some permutation, and maybe I should highlight that every permutation is equally likely. Every permutation has exactly the same chance. So let's make it 3. So I can write them down. So we have 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, and 3, 1, 2, 3, 2, 1. These 6 permutations. That again I disturb you to see, but and the big trick here is don't try to guess anything about what are the different conditions that depends on that I pick the first number and then the second one. Don't make it a backward analysis. Don't make it a conditional probability.
Would it be 50% for both the 3 case and the 4 case?
It will be 50%, that's correct, but why?
Because if you have a 1 first, all of the combinations make it go up because you have the lowest number first. If you have the 4 happens first, then you have none of the cases where it will be updated second.
Don't make it case analysis. 50% is a right condition. By the way, we can actually check it very clearly, maybe at which, since I'm only looking at the first case, that's just a proof by example, and just for I equal 2, then in 1, 2, and and 1, 3, and 2, 3. These are the three cases at which the permutation goes up. The first is smaller than the second, and in the other case it goes down, but there is something deeper than it. All you need to know is all permutations are equally likely, and the second number that I picked is different than the first number that I picked. I picked a number, then I picked another number. The way that the permutation is arranged has nothing to do with how I access them. I'm not necessarily accessing the smaller one or the larger one. I'm picking the first element in the array, then the second element in the array. You picked two numbers at some order. You are not biased toward picking them in increasing order or picking them in decreasing order. The chance, it's just out of symmetry. The chance that the second one is larger than the first one is exactly the same chance that the second one is smaller than the first one. You pick two different numbers, pick them at random, the same experiment with the case of the first loop that I wrote. When we picked number between 1 and n. We just picked two numbers, both between 0 and 1. What's the chance that the first is smaller than the second? It's the same chance as the second is smaller than the first. But just symmetry. You can also, by the way, the case of only two numbers, it will not help us for more than two numbers, but if it's just two numbers that I pick, let's call the first one x, let's call the second one y. I pick two numbers x and y. It's just like picking a point from the square between 0 and 1. But pick a point between 0 and 1. What's the chance that x is smaller than y? If x is smaller than y, then you are at this part, or at this triangle. The point that you picked is in this triangle. If x is, if x is larger than y, you are in this triangle. If x is smaller than y, then you are in this triangle. So here you see why it's 50-50%. But if I pick number at random, it doesn't matter if the numbers that I picked are very large or very small. The only thing that matters is that I'm not biased toward picking the first one as a smaller or picking the first one as a larger. There are just two different numbers. The chance that the first is larger than the second is exactly as the probability that the second is larger than the first. So the probability that the second number that we picked is that we update the number at the second step is exactly 50%. Everybody feels convenient about what I said? Just symmetry. We are not biasing toward this one or this one. Fantastic. Let's switch color. What's the probability that I update the counter when I equal 3? When I pick the third number?
Um, 25%, half of the half.
I mean, my numbers are actually anything between 1 and n, but if my numbers are just 1, 2, 3, just for intuition, 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 2, 3, 1, and 3, 1, 2, and 3, 2, 1. So at which case do I update the numbers? Just if the last number that I picked is 3. If my numbers are only 1, 2, 3, then the only chance that for I equals 3 I update my numbers are only if the last number is 3, which out of the 6 cases happens in third of the numbers. That if my numbers happens to be 1, 2, 3. But if I have n numbers, what would be the probabilities? I'm asking, my array contains n different numbers. What will be the probability?
I was writing down something on a paper in case that the order of the numbers is random.
The order of the numbers at random, every permutation is equally likely, yes.
Maybe it's really off, but it's 1 over 12 n by n minus 1.
It should work for right here, but no. The answer, it's you don't need a paper, you don't need any calculation, you don't need, you just need to think about it in the right way. And by the way, it's the same question had I say I'm picking the number at random, and I'm just sure that I don't repeat the same number twice. So I'm picking 3 numbers at random. They are different than each other. What's the probability that the last number that I picked is larger than the previous 2?
Is it just like 1 over n? So that if you have 2 it's 15, you have 3 over 30.
Fantastic. It's 1 over 3, always. Very hard to see. The answer would be 1 over third because, okay, we need to retire this guy. Look, you have a set of 3 elements. One element, another element, and third element, which is the largest among the 3. In the 3 elements that you picked, one of them is a maximum. In the 3 elements that you picked, one of the elements is a maximum. What is the probability that the maximum one is a last element? It's just out of symmetry. It's exactly the same probability that the middle one is a maximum, which is exactly the same probability that the maximum is the first one. The maximum happens to be in the first. The maximum doesn't have any magic power. I'm placing 3 balls into 3 cells, and one of these balls is special. Okay. This is a red ball. What is the chances that the red ball happens to be the last cell? It's same probability as that the red ball is the first cell, same probability as it is that it's the first or the middle or the second. It's exactly the same chance, just of symmetry. Everything here is equally likely. Any permutation is equally likely, so in exactly the same number of the cases, the last element will be the first, or the last, or the first. So the probability that M is updated when I equals 3, this probability is exactly third. Everybody agrees? You are scrambling 3 balls, one of them is red. What's the chances that the red one will be the rightmost one, or is exactly the same chance as that the red one is in the middle, the same one as that the red one is at the beginning. It doesn't matter who are the 3 numbers that you picked originally, just matters is that every permutation of these 3 is equally likely. And Caleb already said, if we are talking about the case of arbitrary I, at the ith step, so now I'm talking about arbitrary I. Now I have I cells out there. I'm throwing the balls into these cells. No cell contains more than 2 balls. One of these cells, one of these numbers is the largest one. But what is the chances that I'm updating M at the ith step? It will happen if and only if the ith number is larger than everybody that I've seen before it. I repeat, I update it at the ith step if and only if AI, that's if and only if AI is larger than any number in A1 ... until I minus 1. Or when I pick them at random, it is larger than everybody that I've picked in the first I minus 1 steps. So in the whole permutation of the first A numbers of A, what's the chance that the largest one, special, there is nothing about the largest, one of these numbers is a special one. What's the chances that the special one is in the rightmost cell? Exactly the same chance that it's in the cell next to the rightmost, next to the rightmost, next to the rightmost, or the leftmost cell. Each one of the cells have exactly the same chance to contain the special number. Special here happens to be the largest, but it really doesn't matter. So at the I step, what should it be? Help? Anybody but Caleb? Because
Just be 1 over I.
1 over I. Remember it. That's a probability that when I pick the number at random order, something happens at the ith step. Here it's a bit of a trivia question because I don't need it for this part. I need for the rest of the lesson today. I don't need it for the rest of the class, but if somebody sees, I'll be happy to hear. What is the expected number of times that I'm updating M? might be a bit better for the grads, but as I'm finding how to switch scenes, somebody should say.
It should be the sum from 1 to n of 1, or from 1 to I of 1 over I.
The chances that I update m when I equals 1, what is the expected work that I'm spending in the case of I equal 1? It's just what's the probability that I need to update m, which is 100%. That for the case I equals 1. What is the expected work that that happens at the case I equals 2? You're asking what is the expected penalty that you need to pay if your penalty is $1, but you're paying it only with 50% chance. If you repeat repeat this little experiment 1,000 times, how much are you expecting to pay altogether? The average, yeah. In half of the times you have to pay, in half of the times you don't have to pay. So the expected value at the second step would be half. What happened in the third step? You're updating m only with probability third. So if you're repeating it 3,000 times, in 1,000 of them you need to pay on average, implying that the expected value at this step would be 1 over third plus dot 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 until the n step, which is 1 over n. So this sum is, somebody? Never seen before. I mean, that's it's not something to guess. It's either you know or you don't. I don't think that you can guess it right now. Nobody knows? Yeah, correct, Chen. Yeah, Chen said it correctly. This is, Amir, what did you say?
Log n.
Ln n. It's log to the base 2 of n. It's ln n plus little bit change. That's a harmonic sum. Those that took calculus might see the correlation between this and the integral of 1 over x. When x goes from 1 until n, is what's the area of what's the area of this function. It's very similar. If you have not seen it before, that's fine. We don't need it today. But we do need it today, this understanding of the probability that the maximum is at end. Linear programming, back to linear programming. We have a few half planes, hi. Let's use just a bit of vector calculus. Nevertheless, let's remind everybody, if I have one vector v, vector, we'll think about it as a few numbers, say alpha, beta, gamma. That will be one vector v, u, which would be a, b, c, three other numbers. Then u dot product v is just take the first two numbers of u and v, multiply them, alpha a plus beta b plus the last number gamma c. But that's just the dot product of two numbers. We don't need matrix multiplication, but it will help us to work with when we work in linear programming. So in the linear programming, and under this notation, I can say that a line would be represented in general as alpha x plus beta y equals, sorry, do it in other numbers. You are accustomed to see line as y equals mx plus n. Maybe that you've seen in high school. Can I represent every line in this form? Are there any lines that I cannot write in this way? Now the set of all the x and y such that m, some constant, times x plus n equals y. You cannot write vertical line in this way, but every line you can write as alpha x plus beta y plus equals gamma. When alpha, beta, gamma are three constants. But you can always go from here to here, but here you can also write lines that are vertical. But if you want to go from here to here, then you'll just have to write, this will be mx plus n minus y equals 0. And if I want to talk about the half plane, half planes hi, usually we'll write it as y larger than mx plus n, or if we want to talk about the other side of this line, it would be y is smaller or equals than mx plus n. But, or we can write it in a similar way, except that now it will be either smaller or larger. Okay, and back to linear programming, we are given LP given n half planes, or in 3D it would be half spaces. In 3D, instead of alpha x plus beta smaller or equals than gamma, it would be alpha x plus beta y plus gamma z is smaller or equals than delta. And that you already feel that it starts to be tiring and we are writing too many things. So we'll just write a vector a vector like alpha, beta, gamma, dot product a vector x. A in just this case is just alpha, beta, gamma. This vector dot product of x. What is a vector x? It's a bad usage of the letter x, but x here will stand. The vector x, x with a bar above it, is just x, y, z. The list of these three numbers, dot product. What does dot product does? Takes the first times the first, plus the second times the second, plus the third times the third, exactly what you see right here, is smaller or equal than some other number delta. And in the LP, we are given n half planes. How do I tell you about a half plane? I just tell you what is a... I just tell you about the half plane. I'll just specify what are these numbers alpha, beta, gamma, what is delta, and of course if I want to be above or below, and a cost vector vector C, which it would be, for example, two numbers C1 and C2, find the point or a point in all half planes that minimizes c dot x c1x plus c2y. I'm looking for a point that minimizes c1, a point xy, a point x, y that is inside all this half plane. We played with this intensively last meeting. Here is the first half plane, here is the second, here is the fourth, here is the fifth, and C1 and C2, I can think about it as a vector that pushes me in some direction, or I can think about it as a line that I'm moving. We did it really intensively in the last class. And so do see the vector if you didn't, do see the video if you didn't. And I'm looking for a point. We figure out that there is always a point that lies inside each and every of the half plane, inside the intersection of all these half planes, and brings the cost function to maximum or minimum. For conveniently, I always look to bring the function to minimum, and remember, if I want to actually care for maximum, I'll just change this cost function C1 and C2 to be a negative value. So the max to maximize is like to minimize the minus times the cost function. Right? So, and for conveniently, you see, I'll say that the cost function that I look for will be the following cost function. I want to minimize a 0 times x plus 1 times y. It will be more convenient, and it doesn't hurt the algorithm, to say that my cost function is 0 times x plus 1 times y, because we like geometry, and in geometry it just means find for me the lowermost point that lies inside all the half planes. People, do you see the mouse? I had problems yesterday. I brought the whole lecture without realizing that they see the slides but not the mouse. What could it be? Let's see, is it visible when I'm opening Twitch at all? Yeah, I see. Let's try a different scene. Wait, is this a new thing, or was it? Is this something new, or you never saw my mouse and nobody until yesterday never complained? In previous classes, was my mouse visible?
That I remember.
No? No, that's not. Okay, that's it. We have to, in this case, we'll go back to old technology, and because I checked it before today's class, and I, at least Twitch did see it. So, one of you help volunteered to help me with Twitch. So that would be something that I need explanation, or with OBS. Both of them. Why sometimes the mouse is visible and sometimes not so. Okay, so we know Twitch today. We'll just use this part, and yeah, we'll just use old style video sharing.
So, when you cast full screen applications on OBS,
Mm-hmm.
the mouse is generally left out of the casting. If you want the mouse to be visible, I think you have to share the entire screen, or like a desktop.
Okay. It's, okay, so today we'll, at least until we'll find it, if you are on Twitch, please move to Zoom, and I'll just share with you the standard Zoom thing. I don't have Zoom, the monitor of Zoom open. Do you see the mouse and the slides now? And we'll manage only with the slides, but then I don't have the whiteboard. Okay, so each constraint defines a half space region in the d-dimensional space. In the 2D that will take most of the class today, we are talking about half planes. The intersection of convex object is always convex, you know it, and in this case, now which camera do you see? You see this strange camera that is a combination of both of them. You still see. Yeah, you know what? In this case, let's have at least the white. If I need the whiteboard, at least you have the whiteboard in there. Okay, so convex intersection of convex region is convex, and last class we discovered why the optimum is always a vertex. Two-dimensional instead of half spaces, we are talking about half planes, and for convenience, we are looking for the lowermost point. The cost function usually is a vector that pushes us, like the wind pushes us in some direction, and we are looking for the vertex that specified this lower thing. And not always, there is not always a solution. It's possible that the three half planes don't intersect at all, but if they do intersect, it's possible that the solution is actually the solution to the linear programming. When I'm asking for solution to the linear programming, I'm asking which point is it that satisfies all the constraints, and as far as my cost function is concerned, it's the optimized point, but only inside all the half planes that I specified. Remember last class we talked about the diet case of every vitamin specifies a half plane, and I want a diet that was the cheapest, and but still I'm getting enough from each and every vitamin. Okay, so any bounded linear programming that is feasible has a unique solution, which is a vertex in the feasible region. And if the wind pushes you just so you land on an edge, then you can pick one of the direction of the edge, and either to the left or to the right. For this C, you started maybe right here. You do see the mouse now, right? Yeah, so you started right there in the middle, the wind pushes you until the wall, and maybe if you follow the wall in one direction, the cost function will work against you, you'll make it less optimum, but if you go to the other direction, you'll either increase it or at least it will stay the same until you hit a vertex. So there is a solution that is a vertex. In 3 dimension, the wind pushes you. Let's take these allergy pills. You don't see me. Never mind. In 3 dimensions, similar thing. Wind pushes you until you hit a face. Then you're following a face until you hit an edge of the face, and then you follow the edge of the face until you hit the vertex. In other words, once you created all the vertices, this is your solution. So you just need to evaluate the cost function in each and every vertex only. So we are, as usual, moving from continuous domain to discrete domain. There is only a finite number of vertices that you need to check to evaluate the cost in each one of them. Okay, in general, what other cases could there be? The solution might be empty. These 3 half planes has no point in common. Just to make sure that everybody understands, there is 1 half plane that lies above this line, 1 half plane that lies to the right of this line, 1 half plane that lies to the left of this line, and there is no points in their intersection. So it might be empty, it might be unbounded. Here, if I'm looking for the lowest point, you have a unique solution. If I'm looking for the highest point, I can follow this direction all the way to infinity. So unbounded, and it can be not unique, but it's still a vertex. But maybe 2 vertices gives me the same value. Wait, you didn't see the last case. Here I'm looking for the lowermost point, and you see that both these vertices gives me the same value, as well as every other point along the edge between them. They are all, if I'm minimizing the height, they are all equally good. We will go back to the simplex algorithm. That's not the algorithm that I'm going to teach you, but it's what everybody in practice uses. Every student in engineering and SIE see it in much earlier steps. I think that it's bad that students in computer science don't see it clearly. It's a fantastic method that solves huge systems of linear programming in thousands of dimensions, tens of hundreds of constraints, and it still runs very, very fast in practice. It essentially says that I'm trying to solve linear programming in higher dimension. I'll start from some vertex, and then the wind, the steepest descent, will take me to another vertex, and then takes me to another vertex. And simplex is a method that helps you move from one vertex to the next one to the next one, and always improve your way. And in practice, it works really, really well. It's steepest descent, but when we are using very strongly that, we saw it in 2D, but in any dimension, your function, your cost function is convex, and your constraints are convex as well. So it's convex programming, and that's what makes the solution much faster to find. If I'm talking about cost functions, that even in the tiny little me, you can still see that here is a cost function that has 2 smallest minima, or usually NP-hard problems have exponentially many local minima, and to decide between them what is a global minima is much harder. Okay, at least if you see the whiteboard, at least see it. Yeah. Okay, so simplex is fantastically fast in most practice application. We have another way. We can ask how many vertices are there in the feasible region. In the feasible region, we forget about the cost function for a while. We say we know that if we'll construct all the vertices, then one of them will give the cost function the minimum value, the optimum value. So let's build all the vertices. Let's assume that n is a number of constraints. Always in the linear programming, n is a number of constraints. In the diet problem, n was the number of vitamins. D, the dimension, is the number of variables